For the fifth lab, I have decided to use everything that I have learned over the course of this class to analyze the motion of a falling slinky. The goal of this experiment was to observe the effects of gravity and drag on the motion of a slinky as it was dropped, and to use this information to help develop a model to predict the motion of a falling spring. The observed motion of the object will be analyzed using tracker and several fundamental physics principles, and compared to a computational model generated using GlowScript. Then, two different position versus time graphs were generated, compared, and evaluated. This lab is based on Newton's second law, from which the position and velocity update formulas can be derived. Also relevant are the gravitational force, which is equivalent to the mass of the object multiplied by the acceleration due to gravity, and the drag force, which is proportional to the velocity of the object and its cross-sectional area. Finally, another important concept is the tension force, which in this scenario is related to the force of gravity pulling the spring down. I created an observational model of the falling slinky using tracker. Measurements were calibrated based on the height of the man standing on the left, which was stated to be 1.75 meters. The y-axis was aligned with the slinky with the negative direction pointing downward. The x-axis was aligned horizontally, with the positive direction pointing towards the right. The analysis of the frames began when the slinky was fully stretched out, before the top was released from rest, and continued until the slinky was fully compressed and hit the ground. The point mass was set at the bottom of the slinky while it remained motionless. Here is the code for the initial conditions. The known variables include the spring's mass in kilograms, which was given, the initial position, obtained from tracker, and the initial velocity, which was 0, because the object began at rest. Also, acceleration due to gravity is set equal to 9.8 meters per second squared, and the drag coefficient for the falling object was calculated through simple trial and error. The first while loop here runs until the top of the slinky reaches the bottom. In this portion of the observations, the force of tension is equal and opposite to the force of gravity, and these forces cancel each other out, which explains why the bottom of the slinky is motionless until the slinky returns to its initial length. In the second while loop, which runs into the last observation, the drag force is included because the bottom of the slinky is moving downwards. The net force during this time period includes the force of gravity and the force of drag. The force of tension is no longer applicable here. Here is my GlowScript model, which shows the observed position of the spring versus the predicted position of the spring. For the most part, the model is accurate in predicting the position of the slinky. However, there are slight discrepancies that arise later in the model. These could come from a number of sources, including potential calculation errors, other forces that were not accounted for in the model, and errors made tracking the points in tracker. In conclusion, why does the bottom of the slinky remain stationary? The bottom of the slinky remains motionless because the tension force of the slinky, which is basically a large spring, is equal and opposite to the force of gravity, which means these forces cancel each other out. Once the top of the slinky hits the bottom of the slinky and the slinky is no longer elongated, that spring force goes away. So the only forces remaining are going to be the force of gravity and the drag force. The drag force is proportional to the velocity and cross-sectional area of the slinky, and is going to be much less than the force of gravity. Therefore, the slinky will fall, and we will observe the motion that we observed in the experiment, where the slinky falls to the ground and compresses again.